Welcome back. So we have seen the general power rule that's a consequence of the chain rule. So the derivative of f of x to the n is the same as n f of x to the n minus 1 multiplied by f prime of x. So when you look at this function f of x to the power n, you almost wish that you just had x to the power n, and then by the power rule it is n x to the n minus 1. But because it's not just x, it is some function f of x. So in place of x, you put f of x, and then you multiply by the derivative of f. And again, this function here is the composition of two functions where the outside function is x to the n, and the inside function is f of x. So the derivative of the outside is n x to the n minus 1, which you have to evaluate at the inside f of x, and then you multiply by the derivative of the inside. Now we now write down two more formulas that are also consequences of the chain rule. So if we take the derivative of log of f of x by the chain rule, this would be what? Well, here f of x. So here, this function here is the composition of two functions. The outside function is ln of x, and the inside is f of x. So you take the derivative of ln of x, that's 1 over x. You replace x by the inside f of x, and then you multiply by the derivative of the inside. And so what we get is that the derivative of ln of f of x is equal to f prime of x divided by f of x. This is known as logarithmic derivative. And the derivative of e to the power f of x is equal to e to the power f of x multiplied by f prime of x. Again, this follows from the chain rule. If you look at e to the power f of x, well, that's the composition of two functions. The outside is e to the x, the inside is f of x. Now the derivative of the outside e to the x is e to the x, and then you have to evaluate that at f of x, and then multiply by the derivative of the inside, which is f prime of x. So this derivative here is by the chain rule again. And to simply put it, whenever we have an exponential function like this, e to the power something, the derivative would be itself multiplied by the derivative of the exponent. Let's look at a couple of examples where we're going to apply these formulas. Let's say we want to find the derivative of ln of x cubed plus 2x. So here we can apply the second formula here. So derivative of ln of something is the derivative of that something divided by that something. So the derivative here would be the derivative of this guy divided by this guy, right? So it'll be the derivative of x cubed plus 2x divided by x cubed plus 2x. Now the derivative of x cubed plus 2x is 3x squared plus 2. So we obtain this derivative. What's the derivative of e to the power 4x to the 5 minus 7? Well, by the third formula right here, we get the following. The derivative would be the same as this function multiplied by the derivative of the exponent. So we get e to the power 4x to the 5 minus 7 multiplied by the derivative of the exponent. Then we get e to the power 4x to the 5 minus 7 multiplied by 20x to the 4. And the derivative of 7 is 0. So we end up with 20x to the 4 e to the power 4x to the 5 minus 7. Okay, so let's say I want to find the derivative of f of x, where f of x is e to the power 2x multiplied by x to the 10 um, plus 8. The derivative of f of x can be found by first applying the product rule. So here the function has two vectors, e to the 2x and x to the 10 plus 8. So by the product rule, it's the derivative of e to the 2x multiplied by x to the 10 plus 8 plus e to the 2x multiplied by the derivative of x to the 10 plus 8. Again, by using a prime here, this symbol here, the quotation symbol here, we indicate that we are taking the derivative of this function. Well, the derivative of e to the 2x is e to the 2x multiplied by the derivative of the exponent, which is 2, multiplied by this. And then here we get e to the 2x, and the derivative of x to the 10 plus 8 is 10x to the 9. To simplify this, we can factor out e to the 2x, and then we can also factor out 2. So if we factor out 2 e to the 2x, then here we get x to the 10 plus 8. Here we're going to get 5x to the 9. So we basically get 2 e to the 2x times x to the 10 plus 5x to the 9 plus 8. Okay, let's find the derivative of y, which is equal to log of 4 e to the 6x minus 7 x to the 8 plus pi squared. Well, the derivative here would be, again, by one of the rules that I wrote down, it will be the derivative of this guy divided by this guy. So it'll be the derivative of 4 e to the 6x minus 7x to the 8 plus pi squared divided by 4 e to the 6x minus 7x to the 8 plus pi squared. What's the derivative in the numerator? Well, that's going to be 4 times the derivative of e to the 6x. Now the derivative of e to the 6x would be e to the 6x multiplied by the derivative of 6x, which is 6. So we're going to get 4 times 6 e to the 6x as the derivative of e to the 6x here. The derivative of the middle term would be 7, 8 x to the 7. Derivative of pi squared would be 0 because pi is a constant. So here we get 24 e to the 6x minus 56 x to the 7 divided by 4 e to the 6x minus 7x to the 8 plus pi squared. One thing I want to point out here again is that when I took the derivative of e to the 6x here, the derivative of e to the 6x is itself multiplied by the derivative of the exponent, which is 6. Let's do another example. Let's say we have f of x is equal to ln ln to the 5 of x squared plus 3. Now this may be a little bit of a confusing notation, but what this means here is that it is ln evaluated at x squared plus 3 to the power 5. So you take the fifth power of ln of x squared plus 3. That's what is meant by this notation. So what's the derivative here? Well, so we have, if you look at this function, you wish that within the square brackets you just had x. So it is x to the power 5. So x to the power 5 is the outside here. So you take the derivative of that. So that's going to be 5x to the power 4. And then you replace x by the inside here. And then you multiply by the derivative of the inside, ln of x squared plus 3. Now, what's the derivative of this quantity? Well, by one of the formulas that I wrote down, one of the three, the middle one implies that this is the derivative of x squared plus 3 divided by x squared plus 3. And so in the numerator, then we get 2x and multiplied by the 5, so we get 10x ln to the 4 of x squared plus 3 divided by x squared plus 3. So again, ln of x squared plus 3 to the power 4, this quantity is written in this notation, even though I would say that that's a bit of a confusing notation. Here's another example. Let's say we want to find the derivative of f of x equal to e to the 5x divided by e to the 5x plus 3. Well, in this case, it is a ratio, so we have to apply the quotient rule. So we square the denominator, and in the numerator, we take the derivative of the numerator multiplied by the denominator minus the numerator multiplied by the derivative of the denominator. So again, if I think of this as top and bottom, then it is the derivative of the top multiplied by the bottom minus the top multiplied by the derivative of the bottom divided by the square of the bottom. Okay, now what's the derivative of e to the 5x? Well, it'll be itself multiplied by the derivative of the exponent, which is 5. So here I get 5 e to the 5x, and then here we get derivative of e to the 5x is 5 e to the 5x, derivative of 3 is 0. So at this point we can factor out 5 e to the 5x, and if we do that, we get 5 e to the 5x times e to the 5x plus 3 minus e to the 5x, and e to the 5x cancels out, and we end up with 15 e to the, because now we just have 3 here, so 3 times 5 is 15 e to the 5x over e to the 5x plus 3 squared. Okay, so I will stop the video here, and I will see you soon.